Hello, and welcome to IoT Builders, a live stream where we discuss a range of topics on the Internet of Things, from embedded devices to cloud services, all from an IoT builder perspective. It is April 5th, and this is episode 23 of our weekly live stream. My name is Dan Gross, and I'm a senior developer advocate for AWS IoT and FreeRTOS. I am joined today by my colleague and co-host, Alina Dima. Hey, Alina.
Hi Dan, how are you?
I'm good. How are you doing today?
I'm good as well. I'm here in the AWS office in Berlin. Looking forward for our conversation.
Awesome, awesome. Yeah, so today we're going to talk about IoT workflow management and execution, and this is a continuation from 2 weeks ago, episode 21. We started talking about this topic, and you gave a really great overview of the project. But we ran short of time diving into details, and so I think taking the time to really step through the code and highlight the sample project is a great use of time. So yeah, I'm excited to see more from that. It's been about 3 weeks since Embedded World, and I think you gave a talk about this project there, and this is basically a follow up to that, right?
Yeah, exactly. So I gave a talk at the Congress at Embedded World, and the topic is, like you mentioned, IoT workflow management and execution. And of course, last time I dived into why we're doing it, why we're choosing this approach, why is this the right way to actually implement a solution. And I think today, and of course, I did a demo last time, which we will continue also today. But today I would
Mhm.
like to focus on diving in the code to show people who are interested how you can actually build the solution, how it looks like, what the components really are, and what the tools that I was using are. So that is the plan.
Great, great. So, yeah, with that, why don't we dive in and get started?
Right. That sounds like a really good idea. So I have shared my screen here, and I'm hoping everyone can see it. Before I actually dive in the code, I just want to show that this is the GitHub repository that that you can have afterwards, that you have access to afterwards, where you can see the entire implementation and have a look at what I'm talking about today. Of course, I have this repository checked out, and I will be using IntelliJ to show you the code and to run a few things. But if you want to run this on your own later on, this is the GitHub repository, and Dan will paste it in the comments as well. So here you've got a little starting guide and a few of the design considerations which I covered last time in our conversation in our episode 21, and the high level architecture, which I will go through in just a moment in more detail before I start diving into the code. But you've got a bunch of things here, and you also have guided steps on how to build and run the project. Because of course, today as we go through the code, I'm not going to build the entire template again. All the AWS resources are built with SAM, so the serverless application framework, and deployed also using SAM. So you have here the commands that you need for that, and also how to test, and what you need to create in your AWS account. And of course, this also links to the steps to actually run the device simulator. Running the device simulator, Docker is available. I will show you that. So it's basically running. The Docker file is available. I mean, it's running in Docker, and it's got a bunch of you've got a bash script that starts multiple Docker containers to run the simulation at scale if you want. So if you have the capacity, you can even run 10,000 or 100,000 if you would like to, of these Docker containers, and simulate 100,000 devices. And if you find bugs, then please let me know. Just write, hey, I've tried this on 100,000 devices, and here's a list of bugs for you to fix. Or even better, just dive right in and fix the bugs yourself. And of course, there's a cleanup script as well, because the simulator is going to create for you the devices. So it will create the IoT things, and it will create the thing attributes and everything, and the certificates as well. And then this cleanup script that you can run later on is just going to go through your AWS account and get rid of all your IoT things. So yeah, you can also clean
That,
up automatically. Yeah, I just
that's
wanted to
great.
show that this is the repository.
Yeah, that's that's in our IoT Builder tools organization. So we have a number of projects in that GitHub organization, and this repo is the project that yeah, that you're going to be talking about. I pasted the link in the comments, so if anyone wants to have a look while we're talking through it, feel free to take a look. It's public.
Yeah, yeah, absolutely. And the link will be available later on as well. Now, without further ado, I would like to dive right in. I do want to say again what IoT workflows are, because I think it's really important for the audience, for the engineers listening to us or the architects listening to us, to know and understand why we are actually talking about workflows. And the reason why we're talking about workflows is that very often when you are operating against your fleet of devices, you've got a heterogeneous fleet, right? So you've got devices with different type of constraints, generally managed, or you would like it to be managed by the same device management platform that you would that you would build yourself. So often all these devices with different constraints are part of a management workflow that involves sometimes communication with other systems to retrieve information about the device, or to retrieve information about the user that the device belongs to, or to retrieve different kind of configuration settings that you later on have to deploy to your device, or even things like validating a firmware image that you as an operator would like to install on the device fleet as a group, and also roll back later potentially from the devices as a group. So because there are multiple different systems, this workflow is sometimes distributed, and when it is distributed, it becomes complex. So performing all these operations, letting the different systems involved in this communication to perform the operations behind the scenes without any kind of externalized coordination, leads to lack of flexibility. It leads to lack of ability to control retries in a structured level, a task level. It also leads to harder, it's harder to implement observability and visibility into the system when the state of the workflow is not centralized, and when the state of the different steps inside the workflow is not centralized, right? So this is the
Hmm.
reason why when you're building a workflow that is more complex than just one command that you need to execute against your device, it might make sense to break this complexity down and model this process as a state machine, and model it with workflow management tools. One of these tools is a tool that we're going to be looking at today, and this is AWS Step Functions. With Step Functions, you have this possibility to manage an externalized workflow, and Step Functions will take care of definition of your workflow. Of course, you have to define it yourself, but it will provide you the tools to define it. It will give you the possibility to orchestrate the steps, and it would manage for you the state input and the state output and the transitions between the different states in your state machine, and yeah, overall also give you tools for tracing. It has very good integration with AWS X-Ray, very good integration with Amazon CloudWatch, so it would give you also this observability at every step in your workflow. And this is something
Yeah.
that we will also look at briefly today.
Yeah, and this, I mean, you were talking about, how this fits in with IoT and devices. So I guess this could fall under the category of, when you have a mix of what people refer to as brownfield devices and greenfield devices, right? You could sort of imagine that there is this fleet that's not all, consistent, right? And so this could help with
Hmm.
that.
Yeah, absolutely. Or even something a little less complex, like for example, you're buying a consumer device that you want to use in your house to monitor temperature, monitor humidity, and also set your desired temperature level, or
Hmm.
set your lighting setup, and so on. And if you buy this gateway, the provider of the gateway ideally would want to facilitate the configuration management for you, right, based on your desired default settings. And ideally, you wouldn't want to actually go through the process of inputting, when you plug your device, having to go through the configuration setup. If you do it when you sign up for the service, for example, you create an account and then you sign up and then you say, hey, this is my desired ambience for my home. This
Hmm.
gets stored in your profile. Then the device gets delivered to you. You plug it in, and ideally, when you plug it in, all this configuration will be deployed to your device automatically, without you needing to reconfigure or do anything. Or if you do a factory reset of your device, ideally also your settings, because the settings belong to your profile, they don't belong necessarily to the device. Ideally, your settings will be reflashed to your device, reconfigured automatically to your device as part of this workflow. But of course, your device doesn't know anything about the user that owns it, right? So the device is the device. You as a user have a profile, but there is a link somewhere, maybe in a third-party system, between the user profile and the device, right? So that
Hmm.
information needs to be retrieved by the platform. I'm calling it the platform in this case, but it's just the device management solution. So it needs to retrieve this configuration, and then based on this configuration, run a few commands to your device, wait for feedback from the device, and so on. This kind of thing, where the fleet can be made composed of gateways. Doesn't have to
Hmm.
be necessarily greenfield and brownfield, but of course, I mean, it's a very valid point. Greenfield, brownfield, it becomes even more important to have an abstraction layer on top of whatever communicates with the device, whatever system communicates to the device, to be able to extend your solution in a way in which you don't have to modify your entire architecture, and you don't have to
Hmm.
build the system from scratch every time you bring a new device to onboard into your fleet.
Yeah,
So
or
this
even
is
have a
more or
different
less the
or have
use
a
case.
different management system for, one part of the fleet and another part of the fleet, which, unfortunately, I think I've encountered.
Yes, yes, this happens very often. Also, decisions around retiring devices, they're not easy to make, right?
Mm,
And that's why you end up, building fatter and fatter device management platforms, and fatter. I mean, monolith at the end of the day. So it's just a
yeah.
monolith that you would be building. So that's why I personally think that it's really good to look at ways to somehow simplify complexity, model it.
Mm,
And I mean, state machines have been used in computer science for a really long time, and they're used in the embedded world for a really long time. And also, distributed systems are modeled with state machines. I mean, calls to
sure.
distributed systems, orchestration, and so on. So it's a concept that we're all familiar with.
Even in,
So
FreeRTOS, our, the open source, real-time operating system, the scheduler, uses a state machine to schedule tasks, right?
Yeah, exactly. And the A/B partitioning for firmware upgrades as a process generally on the device is modeled. This entire thing of the device initially downloading a new firmware image, afterwards attempting to install this image, and then attempting to boot into the new image, falling back to the old image. It's also a state machine, right? So this
Mm,
entire flow of actually executing all of this it can also be modeled as a state machine. And the same goes with installing applications on devices and rolling back application versions. This can also be modeled as a state machine. So a lot of what's happening in distributed systems, with multiple systems communicating, or with um, you know different stages of state
mm.
in various systems, can be modeled with a state machine.
Yeah. Yeah, that's great. Okay, let's dive in
Right.
here.
Yeah, so let's dive in. So what I will do first is I will walk you through the architecture that you will see today in the code. And so that it makes, I mean, when I start talking about the code, you will know when I say the entry point, you will know what the entry point into the system is. When I say the state machine, you can visualize it as a component. So that's why I actually want to walk you through the architecture. This architecture is also available. The architecture diagram is also available in GitHub, so you can look at this later. You don't have to necessarily take pictures and so on, or come back to the video. Right, so what we're going to be modeling today is a firmware upgrade process as a state machine, and a state machine modeled with AWS step functions. So what we're going to do is we're going to have a manual trigger. So imagine me as I am the operator today for all of you. So I will be, triggering a firmware upgrade on X devices. I mean, I will start with one device later, but then maybe extend it to 100 devices. So I will want to create this firmware upgrade request, and then send the request to start the firmware upgrade on my 100 devices, and let the system that you see in the picture execute this firmware upgrade flow on my 100 devices. So the first thing that will happen is that the firmware upgrade request will come into this component, which is, I've called it jobs processing and scheduling. So this is nothing more than an implemented task scheduler concept, right? So in computer science, you have schedulers. It's a known concept. Schedulers just basically queue tasks for execution. Now, the interesting thing about the implementation of this scheduler, it is taking a firmware upgrade request, but this request can target either one device, or it can target a group of devices. The technology behind the scenes allows also for grouping of devices, because it is built on IoT device management and IoT jobs. So with device management, you can group devices in thing groups, and you can create static or dynamic thing groups based on different thing properties. So this scheduler component would take the ARN of a thing. So the ARN is the resource identification that AWS uses to identify any AWS resource, right? So you have an ARN for a thing, you have an ARN for a thing group, an ARN for a Lambda function, everything has an ARN. So you would pass either the ARN of one AWS thing or the ARN of a group to this Lambda function. And then what will happen is that this Lambda function is going to use something that we call a job template. Now, the job template is really, in this scenario, it's really simple, right? It's saying, start a job that is a firmware upgrade with a state machine name, right? Because, of course, in your system, you can have multiple state machines, multiple workflows. You can have a configuration management workflow. You can have a firmware upgrade workflow. So the state machine will be present in the job template, and of course you can pass any other properties that you want regarding the operation that you're trying to execute. So based on that template that is created, and I will show you the template, it is created via CloudFormation, actually via SAM, via a SAM template. This Lambda function will create a job based on the template, and it once the job is created, this is where the magic happens with AWS IoT jobs, because IoT jobs, when creating a job targeting a bunch of things, you will see that IoT jobs will publish messages on the job designated topics. We are using here Notify Next because we want to have a staggered way. We don't want to allow users, operators, to start multiple firmware upgrades against the same device while another firmware upgrade is running. So we want to basically say, hey, if another firmware upgrade job is started on the same device, just put it in the queue. This is listening to this Notify Next topic basically means that you would be picking up the jobs to be executed in order. They would be queued, and you would be picking, whatever is behind this topic, listening to this topic or subscribing to this topic, is going to pick up items from the queue as they are being populated by IoT jobs, right? So then you have here a rule, so an AWS IoT rule, which is subscribed to this jobs designated topic. And again, we are using the Notify Next topic, picking up the event that is pushed by AWS IoT jobs. And then as an action to this event, a workflow will be started. So here there is at number 4 on the diagram, you would see that this is the automatic integration between the rules engine, AWS IoT rules engine, and step functions, right? So
Mm.
you know that from an IoT rule, you can automatically trigger a step function. I mean, surely you can do it via Lambda, but there is no need to call a Lambda function because there is this native integration that the rules engine has with the workflow management solution, in this case, step functions.
Yeah, and this
Um,
is mostly all
right.
built into to the different service components. So yeah, it's actually using the services as they're intended in a way.
Right, exactly. So this here is automatic integration, configuration, creation of a rule. I will show you the SQL statement and everything. This Lambda function has a bit of custom code to specify, hey, this is the template, create me a job based on this template, and please target either one device or multiple devices. If you're targeting a thing group, the magic, excuse me, the magic of fanning out to all these devices in the thing group is happening by IoT jobs publishing
Mm.
messages on multiple notify next topics, one topic for each device, right? So here you don't see it in the diagram because it would be too much, but there is quite a bit of fan out happening here if if we're dealing with a group, right? So
Mhm.
the fan out
Mhm.
is literally the fan out is happening at the publish step, right? So here you instead of one publish, you would have n publishes, and then the rule will pick them all up and kick off n workflow executions, right? Now, the workflow execution itself, you see it here. This is a step function workflow. We will go through this in detail in the AWS IoT, in the AWS Step Functions console, but it is a bunch of tasks. You don't see it here, but some will be executed in parallel, some will be executed sequentially. One thing that I did mark on the diagram is that the first call that is happening is to check if the device is online or not. Now, for checking if the device is online, we have the automatic SDK integration of step functions with the AWS IoT SDK. So here, you don't have a Lambda function in between because there is a way to configure step functions to say, hey, make a call to the indexing, to the search index with this particular thing name and, bring me back the result of that, right?
Mm.
It's really
Mm.
powerful because and I think it's something that when I used step functions the first time, I believe this was not available. So this native integration at SDK level between a task in a step function and the actual AWS service was not available. At the moment, it is
Mm.
not available for all the calls, but it is available for quite a few in the AWS, of the AWS IoT SDK. So you've got the indexing search, you've got describe thing, you even have create thing, create certificate, you've got execute job, and a lot of others. One that is not available and that would be great to have is actually the IoT data plane, the publishing of MQTT
Mm.
messages onto devices. So there you still need to go through a Lambda function, and you will see that later. But because the native integration is, the SDK integration is not available yet. But, if you would imagine that this is useful, then you can always leave us the feedback and we can escalate this feedback to the service teams.
Now does that leverage,
Right.
now does that leverage shadows, or is that, something aside from, shadows?
So this is something aside from shadows. So
Mm.
this is simply the SDK integration, and I can show you how this actually looks like really quickly because you asked. So you've got a state called get device, and then you specify here that you are dealing with an AWS SDK IoT search index call. It's
Mm.
almost like it's a plugged in API call that you don't need to actually make with a client because the step function task is going to take care of being the client in this communication and making the search index SDK call to the AWS IoT service. And you have
Mhm.
to pass the parameters which look exactly like the API call parameters. You have to pass the query string thing name. So this is kind of how it looks like.
I
And
see.
there is a list, and I think I used to have it here. So there is a list of the call other AWS services. So here you have the optimized integration and what level of support is available for all the AWS for all the other AWS SDK for the SDKs of the other AWS services, right? So this documentation will give you, it's a lot of services, but it also gives you a list of unsupported actions. And here you see that there are a bunch of AWS IoT unsupported actions, but also, the action to actually publish based on the IoT data client is not available yet. Right. So if we go back, we will go into the detail of every step of the workflow, so don't worry about that. But what happens next, right? So somewhere in the state machine, there's going to be a task that will make a call to actually kick off the device management component and say, now send an operation to the device to start the firmware update, right? So this is happening somewhere here. But what is interesting is to notice that this is not happening in a coupled manner, but quite the opposite is happening in a decoupled manner. So what this means is that we're using SNS in between all of these components. And when the workflow management wants to kick off an operation on the device, it's going to pop a message onto an SNS topic. And that message is going to have a Lambda consumer on the device management side of the equation. And this component is going to be listening explicitly for messages that have a particular key in the message body. So it's not going to be listening to all the messages, but just for those messages. It's going to be consuming only those messages to kick off the flow. Now, you might be asking why we're doing this decoupled, right? Why we're not simply, it wouldn't be so hard to have a Lambda function here, simply publishing a message on an IoT topic where the device is listening to. But the benefit of actually decoupling this is that you can later on replace the need, right? So imagine that you have a device where MQTT is not the communication protocol, right? Imagine that device is speaking, I don't know, CoAP, or it's maybe HTTP, or maybe AWM to M, LWM to M, or whatever other protocol, right? If you want to build that in, you don't want to have to modify the execution, the workflow execution, and modify device management. You want to actually just say, this component here stays the same, right? So here it doesn't matter if my device speaks MQTT, or my device speaks LWM to M, or my device speaks CoAP, or my device speaks I don't know what. This is the problem of the device management component, right? So I'm just pushing the problem away and saying, when I want to extend my architecture, I'm not going to have to rebuild this and rebuild this. I'm just going to have to rebuild this, and the rest stays pretty much the same. It also helps with scaling, right? Because this is, at the end of the day, a fan out. Decoupling in complex architectures is always a good idea. So this is what this component here achieves. So when this message gets sent on SNS, if it is a message that involves interacting with an IoT device, like, for example, start the firmware update operation, then this Lambda function that you see here is going to consume that event. Now, you will see that Amazon SNS recently introduced this feature of topic filtering, which is super convenient, because you don't have to, when you configure your consumer, when you configure AWS Lambda as a consumer, you can specify what particular messages based on particular keys, either in the message body or in the message attributes, you want to be listening for. So this means that this Lambda will only be invoked when a particular message type is received by SNS. And this is all configuration, which is also great because it reduces the number of lines of code to actually write and maintain. So when the Lambda function receives this event, what it's going to do is it's going to parse the event to understand, okay, well, now I have to send an over-the-air update operation asynchronously to the device. Here, the implementation you will see further regarding the communication between device management and the device is actually very specific to the protocol that I have implemented as a communication protocol between device management and the device. And here we're talking about TR369 as a protocol, which specifies sending protobuf over MQTT instead of JSON over MQTT. And also, this protocol basically specifies that messages to set configuration or to trigger operations are sent, even if they're sent as a pub sub pattern. At the end of the day, they need to be wrapped into a request response. So because pub sub needs to be wrapped into a request response, and because we want to receive the response synchronously, now the response in this case is going to be just if the device accepts the operation or if it doesn't accept the operation, right? But still, the device, once it receives that operation message, it parses it, it looks at it, it decides if it wants to do it or it doesn't feel like doing it. And if it does want to actually accept the operation, it would send an acknowledgement saying, yes, I'm accepting it. But as you see, the device sends it on a response topic, right? But here somewhere, we are waiting for that response, and we need to correlate it to the request. This is the reason why you see that the AWS Lambda function is, subscribing using MQTT over WebSockets for a very short time. So this is not meant for an ongoing MQTT connection between Lambda and IoT Core, right? So this is the span of maybe 1 millisecond, 2 milliseconds until the device responds. It will time out, and it is okay. So it is also configured to time out a lot faster than a 24/7 communication channel, right?
Because it's supposed to be synchronous, but we're using an asynchronous protocol, MQTT. So it's kind of like you said, wrapping it in a synchronous way. Yeah.
Right, exactly. And this is used in automotive. You'll see this quite a lot, of this kind of pattern where pub sub is wrapped into request response, into HTTP request response. Because if you want from the outside to set a particular setting onto your car, I don't know, entertainment system, for example, you care if it's done immediately. If it's not done immediately, you can run the command later. So if the ECU of the car does not respond right away, then what will happen is that you can forget about your request and you can just simply say, hey, it hasn't worked. So you can easily imagine an HTTP API saying, hey, set my sound system to really loud, and either that is successful or is not successful, but the device still talks pub sub, right? It still talks MQTT, but this MQTT pub sub is wrapped into HTTP request response on a higher level when an app is trying to make these calls. So you will see this pattern. I would say it's what needs to be done in such cases, right? But going back to our problem at hand, once the device sends the acknowledgement that it has started the operation, again, the device management is going to publish saying, hey, operation accepted. And this feedback is going to go back into the step function to terminate any wait state that was waiting there for an asynchronous message from the device. And once this asynchronous operation to do firmware updates has been kicked off, ideally, the device would send a bunch of events to indicate whether it has successfully downloaded the firmware or whether the firmware download has been unsuccessful, whether it has successfully finished the installation operation or whether that has not finished successfully. And eventually, ideally, and I will explain this ideally later, the device would also inform about the boot event where it has either successfully booted into the new firmware image or it has failed to boot into the new firmware image, remaining on the old firmware image, which basically means that the device rolled back. So if you get information that the device rolled back, you might want to actually roll back the entire workflow that has happened before if there is anything regarding consistency that you might want to roll back. So this is also quite interesting. Now, of course, I am aware that some device management protocols, especially lower level ones, don't support that the device is so chatty with a device management platform. If the device is not so chatty and all you get back is, hey, I've done the firmware upgrade or I haven't done the firmware upgrade, then of course you can modify your steps accordingly to wait for fewer messages or to simply for a particular device type skip any other state that you might have for other types of devices. Or even better, you can start building the simplest firmware upgrade mechanism that is supported by your entire fleet, and then add extra steps on the fly based on devices that are supporting more granular feedback from the device side.
And
Right.
this can be if an IoT device goes to sleep for a little while or something like that too, right?
What's interesting, very good point, Dan, because if the IoT device goes to sleep in the middle of this flow, and this flow would have been just a one command from the device management platform as a fire and forget, then there would be nothing waiting to receive the feedback from the device when the device comes back online. You can configure your workflow execution component here. So you can configure the state machine to wait because it's time to rotate the certificate, right? So this is another example.
Yeah.
If there is if there is intermittent connectivity and the device loses connection and comes back online, you can configure your task to time out, and I will show you how to time out a little later. So that's possible. This is another benefit of actually externalizing this workflow management. Right. So this is how it works on a high level. So now I think we should go into the code because we are running out of time again, which we don't want to. So let's see. Let's look first at the entry point, right? So we said that the entry point is creating this job, right? So you see here that my code is structured based on the components that you saw on the diagram, right? So you've got the device agent simulator, you've got the device management component, you've got the job processing and scheduling, which is the entry point into the system. And then you've got the workflow management and execution as well. So first, let's look at the job processing and scheduling, right? So here you've got the Lambda function that creates a job based on a template. So now this is a very simple JavaScript Lambda handler that simply receives an event, and the event looks a bit like this, right? So what is the firmware version you want your group of devices or device to go to? Is this triggered manually? Now this is only introduced for more information around the trigger, because you could have potentially automatic triggers. For example, when the device comes online the first time, you can trigger the automatic firmware upgrade for the device to actually go to a certain firmware version if you would want to. For now, we're going to play around with a manual trigger only. And here you have the target arm, right? So this is either your device or your group of devices. Right. So here what's happening is that this job service is called. So we've got the service class because we didn't want to overload this Lambda handler. This is just the coding style. You, of course, can do it in one function, but it's not recommended. So here you are creating a job from the event based on a template, and this is the create job call. Now, once this is called, and once this await happens, right? So once the asynchronous behavior is finished and the job is created, you will already see the fan out, right, happening on the job site, because messages are going to be published on the notify next topic, one message per device, don't forget. So now this is the function that creates the job. When the job is created, remember, and messages fanning out on the notify next topic. Now let's see in the SAM template. Let's have a look at this function, right? So this has to be something with job. It's not job update because this is updating the job status. It should be job create. So this is the job create function. I want to show you, how this function is configured. So I am using the serverless resource. So I'm using SAM. The actions, of course, create job, describe job template for the job template, and these resources that actually should be based on permissions on the list privilege. One thing that I do want to mention about this is because every single time I'm actually coding list privilege in CloudFormation or in SAM or in any other language, I find it really hard to come up with this ARN, and I have to constantly go back and check the documentation. I have found a very nice documentation page that is really useful for IoT resources, right? So this page here, so this is under service authorization latest list AWS IoT service actions. So this specifies the action, but also the resource, the resource type that actually is required for the permissions, right? So if you look here, you can come up with the ARN by just checking the type of operation and checking the actual resource that is affected. And one interesting thing that you will notice is that if you do describe endpoint is a read operation that doesn't have a particular type of resource, which is also quite interesting. So I would recommend using this. I mean, it has helped me speed up coming up with all this different resource ARNs for the permissions and for the policies. Right.
I can put that in the comments here. Let's make sure I got that right.
Yeah.
Yeah, there we
go.
Yeah,
cool. Thanks.
Cool.
Yeah, thanks, Dan. Cool. Yeah. So now, as a next step, I think we should look at what happens when a message arrives on the notify next topic, right? So IoT Jobs as a service is going to take care of publishing the message on notify next. And now we're going to be looking at what we do, right? So this is the rule, which is called start state machine. I mean, it's not surprising because this rule actually kicks off the workflow execution, like I said earlier. So this is actually going to start the state machine. Let's make this a little bigger. So this is going to start the state machine execution. And here you can see the SQL for this. I will explain this part as well because this is also interesting. So the SQL is actually relatively simple. We do want to extract the thing name from the topic name. So always this $AWS, so this starts at 1, right? So you've got 1, 2, 3, and this is where your thing name is going to be coming in, right? So when IT jobs fans out, here is going to be your client ID or thing name in the topic name, right? So you will see multiple messages based on the different client ID. You do want to pass to the step function, you want to pass the thing name as an input into your workflow. So that's why we're storing it separately and adding it to the payload that already comes from the IoT job and from the IoT job template. Now, notify next is interesting because I told you how it queues the tasks, right? So tasks are queued for execution. But of course, the job service, when a task finishes execution, it will also publish a message on notify next saying, hey, this job is completed, right? So notify next shows starting a job. You get a message when you're starting a job. You get a message for a status update, and you get a message for indicating finalizing the job. But of course, that message is going to come without an execution object because the execution is done, right? So this is just to notify that, hey, I've closed the loop. This execution is actually done. But we don't want to start the workflow for that, right? I mean, we don't want a state machine to actually start when the execution has finished, right? So we want to ignore anything which doesn't have an execution object in because we don't care about that. This is the
we
reason
just
why
care
we've
about the
got
state.
this square. Yes, exactly. We care about when we are trying to start. That's what we care about, right? So this is basically how the start happens. So this rule will get executed. It will, of course, there's a role, to allow to start the step function and the name of the state machine that you're trying to execute as well, right? So now I think as the next step, we probably should have a look at the state machine itself, because if we remember from our diagram, the next step that happens here is a walk through the step machine, the step function state machine. So let's see. For this, I think I'm going to go into the step function. I mean, we can walk through this, and maybe actually let's do this for a change, right? Let's not walk in the AWS console. Let's just go to the JSON file of the state machine and look through the states of the state machine, right? So this is JSON format. If you're trying to model a workflow, I would really recommend using the design inspector. So Step Functions has the inspector, which is a visualization tool for you to start creating the different steps in the step machine, in the state machine, and configuring them and so on. And it's quite powerful. At the end of that, you can export your JSON and use it in your application if you so wish. If you want to write this JSON file, I mean, the other format supported is YAML as well. If you want to write JSON or YAML, you can also do this, and it's no problem at all. Right, so start at indicates, of course, the starting point of the state machine, right? So this is get device. Now, get device is important because what we really want to check is if the device management solution platform, meaning the AWS registry in our case, knows about the device that is being passed into the firmware upgrade request, and of course, if the device is online or the device is not online. If the device is not online at the moment, it doesn't make any sense potentially to start the firmware upgrade yet because the device is not online. So here, of course, this is the logic that I have implemented in this state machine. You can modify it. So if you don't care if the device is online or not, then you can skip this step. But in any case, this is a task, and it involves, like I said, the SDK, IoT SDK integration with the indexing service, and passing in the thing name and getting the result if the thing was found or it was not found. Now, the interesting thing about step functions is that you can specify that the input into the state is added to the output after the execution of whatever the task is running, right? So if the task is running the search index and returns the thing together with the thing attributes, you can add this to the input into the state and create an output, and you can manipulate the output to your convenience. I mean, here I'm just saying with a result path, hey, add the result of the indexing service search into a key called result into the JSON object and add it to the input the input into the state machine that came from the rules engine, right? Including the thing name. Because the rules engine kicks off the state machine, passes the event as input. The event is the job execution object with the thing name, and at the end, the result of the indexing search is added to that. What's interesting is that, of course, SLAs on AWS IoT data plane, control plane come into play, and you might want to build some retries here, right? So if you have large scale, if you do, let's say, 100 devices, you will definitely have more than 10 TPS coming into the search, the indexing search. If you've got more than 10 TPS, you can, of course, increase your service limits. You need to model your load. This is what I recommend to all the engineers who are trying to, design something that goes for scale. Model your load. It doesn't matter how you do it. And then increase the service limits. No matter what the service limits are, it's always good to have a retry in place. Now, this is nice because you see, this is the benefit of actually modeling a state machine, right? With step functions. You actually can specify a retry designated and dedicated only for get device as a state. So you get really granular, saying search index needs to retry basically twice with a backoff rate of 2 at an interval of 4 seconds between each retries. Right. And there is a lot more than you can actually do, right? You can also add a timeout, but I mean, there's no need to actually add a timeout for search index. But of course, you have a lot of opportunities to go very granular and to go very deep in your configuration. So again, the next step is whether the device is found. So this is a choice state, right? So has the indexing service found the device? Has it not found the device, right? And here, this is based on the API call response. If things exist and if things have 0, you always have one thing with the same thing name in AWS IoT. So you're never going to have more than things of 0 here. The array is always going to have one thing, but it might also not have anything. And this is why you're checking if things exist. And then if things of 0 is true, and if yes, then you go to evaluate device, right? So this is a choice state. If the AWS IoT registry has not found the thing, then you're going to go to publish failure to start. Now, publish failure to start is putting the feedback onto the SNS topic so that it can be passed by the IoT jobs to close the feedback loop, right? So imagine you start the job on a thing and the thing is not found on the device registry, then or the thing is offline. Then you're obviously going to want to close that loop, right? So your job does not continue in progress indefinitely. It's nice, right? It's nice for the job service. It's nice for the overall solution to actually close the loop and complete. This is why we are going to publish this information. Right, so let's see what happens next, right? So the next is evaluate device. So this actually checks if the device is connected. So here you have the same pattern. The device is already present, right? Because you did a search index. So the search index gave you the device. Then you're looking among the MQTT connected events. If the device is connected, then it's good. So if the connected flag is present, then the device is connected. Now I'm looking at this and I think that this is actually double here, unless I am seeing double, which is also possible. This is probably one check too much. So we will get rid of that. I mean, it would have been true anyway, but see, spotting another error. And then we're moving to the device connected state, right? The device connected state is just passing. It's a pass-through state saying the device is connected. Device not connected is, again, returning false. The reason why we want to do this is because we want to end the result of the indexing search on the device and the result of actually whether the device is connected. So if the device exists in the platform, in the registry, and the device is connected, then we are going to check if this is the case. It's again a choice. And if this is the case, we're going to go and set the firmware upgrade possible flag after we validate anything else like the firmware version or whatever we want to basically say, hey, the device exists, it is connected. The current firmware version on the device is less than the desired version. We have a firmware version attribute on the device, so we can upgrade, so we can start the upgrade, right?
Yep.
This is what this state looks at. So it's looking at the results of the firmware version, thing name, thing ID, and whether the device is connected. So after this choice runs, then we know whether we can start sending the download operation to the device or not. If we can't, then again, we need to send the feedback back into IoT jobs and close the loop.
Mm.
And this is what this publish failure to start does. Again, here, very nice SDK integration with the SNS API. This is very nice because it makes, I mean, I don't have to write a Lambda function to integrate a task in a step function with SNS to publish the message on SNS. I can just do it here, right?
Yeah.
So I pass some parameters as to what I want to do, and this is what is going to happen. Now, the next step is actually very interesting because here we are starting the download. Now, the nice thing about step functions, and this is something that is true for the standard workflows of step functions. So step functions has support for standard workflows, and it also has support for express workflows. Express workflows are workflows that happen very fast, right? So theoretically, it would be nice if you could wrap that fast request response that I was mentioning here, if you can wrap it into an express workflow. However, express workflows don't support waits and they don't support callbacks. Because they don't support callbacks, then you have no mechanism to actually wait for the response from the workflow itself, right? So
And that doesn't
this
work very
is
well when we have this asynchronous MQTT. Yeah.
No, it does not work very well in this particular case. The benefits of an express workflow would be phenomenal, but it's again, if you have this use case where you want callback support in express workflows, do put a thumbs up on the video, write a comment, and we will take this. I mean, the more the merrier, because you know that the AWS service teams always build features based on feedback from the community. So if you need that, I personally believe it would be nice to have, but if you also think so, please put a thumbs up. So that's why this is why we're using a standard workflow instead of an express workflow. I mean, of course, this and the fact that based on the different types of workflows that we're implementing, we might want this workflow to survive for a really long time in the cloud, independent of what's happening with the device, having to reboot 10 times, or the device going offline, or running out of battery, or whatever might happen, right? But still, at times it would be valuable to have these express workflows with callbacks. In any case, this is how you do a callback, right? So here, the SNS publish SDK integration into step functions is also waiting for a callback. So we literally publish on SNS, and we're saying we're waiting for the callback. Now, the callback is what happens on the device saying I've accepted the start download operation. Right? So what happens when you specify wait for task token is that on entry into the start download task, already on entry, step functions creates a token and passes this token in here for you to manipulate as you see fit. At the same time, this task remains waiting until something external, potentially, would pass the same token back and say, terminate the task that is waiting with this task token, right? So you've got a token coming in, you do your stuff here, this state actually waits, and then externally you would retrieve that task when the time is right, when the device sends back a message, and you would use that task to actually terminate the wait into this particular step. But of course, here in this case, this makes a lot of sense because the device, you remember that we've used this MQTT over WebSockets. So here we are wrapping this communication into a synchronous call to the outside world, right? Because to the outside world, it's here we've got this Lambda function literally publishing a request and subscribing to the response topic and waiting for the response, right? So this is kind of wrapped into something that looks to the outside world as synchronous, no matter what happens inside here. So here we would have no problem terminating with the task token because the response would come relatively synchronous. But let's move on because you see that the next communication is fully asynchronous, right? So here events will be popping out of nowhere into the AWS platform. I mean, obviously not out of nowhere, but for someone from the outside who doesn't know that a request was sent, suddenly you just have events popping, on AWS, on MQTT topics that need to be handled, right? And so after the start download was completed successfully and the device accepted to actually execute this, we know that so once we are out of this state, we know that the device has started the firmware upgrade process. And now what we do is we are waiting for feedback, literally. So we go into 3 parallel states. And the 3 parallel states are basically saying, wait for device messages, right? So we are waiting for a device to send an event called firmware transferred. And we are waiting for the device to say, to send another event, which is operation complete. And we're waiting for the device to send a boot event as well. I mean, this is how this state machine is implemented. If you have a different device protocol which doesn't support this granularity, then you can build it differently. So I'm not going to go into the detail of each of these wait states. Because they are all the same, but I will go into the details of one of them, right? So let's look at the firmware transfer, right? So this is a wait for task token. However, here you see that there is, here we see that there is a DynamoDB put item SDK integration call. The reason why we are going into this wait state with a put item into a DynamoDB table is because in this scenario, the callback happens, going back to the architecture, it happens via the rules engine, right? So it happens again on the response topic, Lambda function, and so on. But where is the token that was created, right? So we enter a wait state, we wait for a message, but the device has no idea that a task token was created, right? So how and where is the link between the task token that was created on entry into this firmware transferred state, wait for firmware transferred state, and the message from the device saying I've transferred the firmware successfully.
Yeah,
right?
you
So
have
that's
to
why
have a
when we
map
enter,
or something.
right, exactly. And this map is actually a database table, in my implementation, this database table is literally somewhere towards the end here. Let's see, it's not very complicated, right? So it is, yeah, here it is, right? So it's called firmware upgrade task tokens. Operation ID is the hash key and token is the range key. So the reason for that is to make the query easier, right? Because the device is going to have the operation ID, because the operation ID is going to be passed the operation ID is the job ID, right? It is the initial firmware upgrade request as a job ID. We pass it on as operation ID. We pass it on to the message that goes all the way to the device because it's an ID. Nobody cares, right? It's an external ID. Putting an external ID into a message is not a big deal. Putting a token into a message, it would be huge. And we also don't have the token available to put it in, right? And the token is the range key so that we can query easier the DynamoDB table later on. So that's how we literally store this. And this is how the put item here, would operate. We are passing the parameters needed by DynamoDB. You also see here that there is a status active on this entry. The reason why we have a status is because, of course, we might want to delete entries. Generally, when I'm working with DynamoDB, especially on production, deleting data is not the best practice. Deactivating old data and putting the TTL on that particular row could be an option. So, keep a status, keep it active at first. When the entire flow is over, or when the message comes back and the state actually terminates, you can deactivate this entry. Right? So this is how this looks like. So we are in waiting for transfer completed, right? So waiting for firmware transferred. We are waiting for a message from the device to terminate the task in the state machine. Now let's look at the function where this happens, right? So the first thing that happens when the device is actually sending back a message is that the device management component is hit, right? Now here you are going to see a lot of protobuf, but I will show you anyway. So the device management component has a message handler. Now this message handler function is the function that receives messages from the device, right? Here, this is the payload that is basically protobuf-like, right? The reason why you don't see protobuf here is because recently AWS IoT, especially the rules engine, has introduced a mechanism to decode protobuf on the fly, right? So this Lambda function is receiving JSON right now because this Lambda function is configured So this Lambda function is in device management, and it is called message handler. Let's find it, because this function is, this is the function, device message handler, right? So this is configured as a function on an IoT rule, and this IoT rule is leveraging the automatic on-the-fly protobuf decoding based on the device management protocol specific schema, which is stored in an S3 bucket, right? So this is going to decode the record and the message. This is really USP specific. You don't necessarily have to understand it because this is device management specific. But the whole point is that the payload is going to be decoded on the fly. This is where the device is pushing the messages, the responses. This is going to be decoded on the fly, and the body is going to be passed into the Lambda function. So this is a really nice feature to have, because otherwise, if the decoding on the fly was not available in the rules engine, you would actually suddenly see binary in here. So you would have to, a stringified version of a binary payload, of course, would be passed into the Lambda function like the old days before this feature was available. You would have to start decoding inside the Lambda function. But right now we are receiving a decoded protobuf, right? So a JSON like protobuf decoded message. But still the structure is pretty weird, right? So this is how you look in the request. You see whether it was a notify, and you see the event name, and we are looking for transfer completed. And we see that if the event name is transfer completed, then we are building this nice message called firmware transferred. And guess what? We are publishing it on the SNS topic, right? And then we're done. Device management is done. But then the workflow management comes into play, right? Because workflow management has to, listen for this, for this firmware transferred, as well as the others, and act on the state, on the wait state based on that. So let's see where this happens, right? So you've got this upgrade status. Actually, I'm going to do something even better. I'm going to copy this firmware transferred, and we're going to find the Lambda function that is the consumer for this event from the from the SAM template. So we see it here, right? Upgrade status received. This is the subscription, of course, but we're looking for, the subscription is actually good. So here is the Lambda function. Now, the reason why I'm confused when I see this is because it is relatively ugly. Creating a subscription as an AWS resource is not nice. Ideally, on this Lambda function, you would actually go and you would put here your desired messages, right? What you want to listen for using SAM. The issue is that SAM does not have native support for subscriptions with topic filter. So at the moment, subscriptions with topic filter from the message body are available in CloudFormation, but they're not yet available in SAM. So that's why here you need to use CloudFormation. That's why it is a little confusing and a little ugly. But in any case, this is our Lambda function that is listening for those events, right? And if we actually go in and we look at what this Lambda function does, so it received this firmware, this event saying firmware transferred. And then what it does is it checks that the message name is present. It checks that the operation ID is present. It checks that the thing name is present. I mean, this can be done very nicely with a validation framework like MIDI. A validation framework like MIDI can validate an SNS message and make sure that all the fields are present. But this is done at POC level. You can definitely improve this code when you're using it for production. And then what it does is it finds the token based on the operation ID, based on the name of what this operation is, and based on the thing name. Once it found the token, then it looks at the status, right? Has the device published on SNS, has device management published on SNS that this transfer was completed with success, or was the transfer completed with failure? If it was successful, then what it does is it terminates with a state machine, with the step functions client. It sends a task command success with the parameters, including the task token and a bunch of output parameters, right? And it terminates in this way the wait in the state machine in the step function. These output parameters seem insignificant, but these output parameters that you pass here are very important because guess what? I mean, they're going as input into the next step in the state machine. So here you can pass, for example, the firmware version that the device booted in to make sure that you update your thing attributes on the cloud side.
Yeah.
So this is what what happens here. But what I also wanted to, so this kind of terminates the loop, like you saw on the diagram, back into the into step functions, right? Back into the state machine. Now let's go on a little bit with the state machine itself. And I know that we actually overran a little, but maybe we can still use the next 10 minutes so I can walk you through a little bit more, at least finalize the state machine, if that's okay with you, Dan.
Yeah, yeah, let's do it. We'll just go over
All
a
right.
few minutes here.
Yeah, we will make an exception to our plan because yeah, it's a lot to tell. Right. So now, one of these wait states has been terminated. In the same way, when the device sends messages, given the granularity of the time interval that it takes the device to finish the operations, all this wait states, the three of them, will be terminating, and then we are going to go into an interpreter state, right? So this interpreter state, let's see where the interpreters are. Maybe it's faster to just look at for interpret. No. Okay, so how is the state called? Boot message received. Okay. Yeah, this is the step. So after each of these events arrive, remember we were
Ah,
talking about invalidating the status. We're doing it with another put item. I mean, of course, this cleanup is not necessarily needed, but it's good because when we are querying, we should query just for active entries. We shouldn't query for inactive entries. But because this is the boot event, we have the update thing, which again is updating with the variable for the new firmware image coming from the output parameters when terminating the wait state. But what I actually wanted to see is the interpreter state. So, okay, so this deactivates. Yeah, even I'm getting confused too much, Jason. These are all the failure scenarios. Yeah, this is it, right? So the is firmware update
is
completed. So
completed.
of
Oh, yeah.
course you need,
Mhm.
and this is when each of these states are basically pushing their results, we're going into a choice to look, has the boot event arrived? Has the transfer completed event arrived and this correct? And has the operation completed been successful, right? So here we are looking into the results of all of those different functions, right? And first we're looking if the result is present, and then we're looking if the status is success. And the status, of course, comes from what I was showing you earlier, meaning this output, right? So we have in here the output parameters, and in the output parameters, we pass the message status, and the message status is either success or fail. This goes into the input of the next step in the state machine, and here we are validating whether it was successful or it failed. But not only one of them has to be successful, but all of them have to be successful for the firmware update flow to actually be successful. If we have success, we are publishing it, right? And again, publishing is going to be interesting. Let's look at it this time, because last time we didn't look at it yet. So publishing success or publishing failure, forget whether it's success status or failure status, is calling the SNS publish using the SDK. And this is the topic, right, that we have. And of course, what we are actually publishing is firmware upgrade success or firmware upgrade failed. Now let's find the Lambda function that is processing this event. And we can see it here. So it is the jobs update status. And this is doing what I was mentioning to you before. This is closing the loop with IoT jobs, right? Let's look at how we close the loop with IoT jobs. Now, of course, because it is jobs update status, it's clearly talking about the scheduler. So it clearly has to be located in the job processing and scheduling component. And listening to SNS, I can show you this on the diagram. It is this Lambda function here that is consuming events when the result of the entire firmware update flow is presented, right? So what happens here is that this update status Lambda function is going to be called, and this Lambda function is going to look at what operation ID or job ID. The reason why it's not a good idea to name variables job IDs, because when they are being passed cross-domain, the workflow management component doesn't know about jobs, right? It knows that it has received an operation with a particular operation ID. This is just basically domain encapsulation. So just encapsulate domain variables based on what the domain needs to know. Don't give other domains information that, about things that they don't need to know. Because if later on you want to change the variable job ID in your device, in your scheduler, what you don't want to do is go through all the other services and change it everywhere just because you changed it, conceptually in one part of your code. I mean, this just comes with experience when coding like large production environment solutions, when one little change that seems meaningless causes so many problems downstream. But anyways, let's not go in there. Let's keep it for another time. Now let's look at thing name and job ID being present. Let's see how the update job execution happens, right? This is, again, the IoT jobs data plane saying, this is the job ID. I have received information that this job has finalized with a particular status. Now let's populate this job execution status variable needed by IoT jobs as a service with either success or fail. And let's send this update job execution command to terminate the particular job with a particular job ID. Now, important, this is the job execution, right, that we're terminating. We're not terminating the full job, because we don't know how many other devices are still pending in terms of execution, right? So operation ID is job execution ID, not job ID, job execution ID. And we are terminating that the job execution with job ID, and that's the particular job ID. And of course, there is also the thing name mentioned there, right? And this basically closes the loop into IoT jobs, and it nicely somehow terminates the entire flow and gives visibility into whether a job was successful or whether it failed. Now, more or less, of course, now it's up to you to actually look at the code, go into as much detail as you need. Ask the questions. If you've got any questions about how any of this is working, you can reach us either by commenting on the video or simply reaching us on GitHub by putting comments and so on. And I will respond. If you do try this on 100,000 devices and you've got some problems or something doesn't work or something weird happens, let me know. So far, I have tried on 10,000 and this was working. And I've tried also on 100 and this was working. So, wow. Of course, when you're dealing with large scale, a lot of things can go wrong. But I would be curious to actually hear what your experiences are with this code. And of course, my plan right now to extend this is to go beyond TR369, because like I said, this particular communication protocol here is very specific. Now, the same kind of thing can be implemented maybe for CoAP, maybe with Meta, with a Meta specification. I don't know what will be next, but here are some ideas. Or even with a proprietary JSON over MQTT implementation between the cloud and the device. This is also an option. But I think it would be interesting to try this with CoAP and to try this with something like Meta and see the kind of challenges that you would encounter in the device management component throughout the way, and also see how your state machine would look like for a protocol like LW M2M. So yeah, let's see. That's something that would come, maybe next in the future. Right. Unfortunately, there won't be any time for a demo. Sorry, Dan, go ahead.
Oh yeah, I was going to say this is excellent. As far as a deep dive into the code and the steps in the step function, it's really great to see. Really detailed the implementation here. This is fantastic.
Yeah. So, my recommendation when working with step functions is to use, the designer as much as possible. And I can actually show you this, right? So when you create a step function, you can decide if it's standard or express, but then you go to a step where, it actually shows you, it presents you with a workflow designer. And here you can design your flow with the states, right? So let's say you want to start with, the action being a Lambda invocation. You drag a Lambda invocation here, and then you say, I want to go into a choice state with the result of my Lambda invocation. And then you go into a choice state, and then you drag. If the Lambda function was successful, I want to publish on SNS. If the Lambda function failed, I want to do something like DynamoDB dynamodb, I don't know, put item. I want to write the request that failed into a database. I
Mm.
mean, something like this.
Mhm, mhm.
And of course, this is not valid. And step functions, of course, the designer loves for it to be valid. So you can't really go next until you specify the lambda function name and so on. But if
Mm.
this all worked, and actually, no, wait, it actually works. So you can export it. So you export it as a JSON definition,
Oh,
and
and then
then you can open the
fix it
JSON
there.
file and then
Yeah.
fix it. This actually helps you not to start with pure JSON structure and write everything from scratch, right?
Mhm.
So it is really helpful. I think it depends on the complexity of your state machine, right? If it's really complex, you don't want to write all the complexity yourself. If it's simpler, then you might want to go straight for JSON. But I mean, this is what I would recommend. Play around with this, and once you've got the most important components in place, you can even specify inputs and outputs and error handling as well. Here you can implement retriers and so on. So you can do quite a lot in this designer. It is actually quite powerful.
Yeah, that is super cool. Yeah, I really like that. Okay, well, great. I know we're quite a bit over time. Anything I guess last minute that you want to throw in here before we wind down?
No, just basically again, the urge for everyone to have a look at this, and provide feedback. If the topic is interesting, the topic of merging in the world of serverless IoT and serverless components and IoT and step functions and all this serverless technologies playing together, do leave us some feedback so that we know what to focus our content on. If you're interested in this topic, if you have trouble with this topic, if there are some specific details that you would want further deep dives in, um, you know, let us know. We are always appreciating your feedback, just the feedback from the community. I do plan one more last thing. Then, sorry for overrunning continuously. I do want to say that I'm currently working on a blog. The blog is going to be about a very, very simple state machine that you can build with AWS IoT and the IoT integration. One that is not of the complexity of the step function that you see here with firmware upgrades, but it has a really small number of steps and so on. And this blog is going to be available in the next days at one point, and the code for it will also be available in our GitHub repository. So again, the same organization, IoT Builder tools. If you want something simpler to start with, have a look there once it's
Sounds
ready. We will
great.
advertise it on LinkedIn and so on.
Yeah, yeah, sounds great. Yeah, I can't wait for that. Okay, well, cool. I think our time is about up now. So really appreciate you walking through all this, Alina. This is really really cool and really great to see the details here. So um, we will be back next week. Our weekly live stream, IoT Builders, will be back on schedule, I think, with 8 a.m. Pacific and 5 p.m. Central European time. We had a little late start today, and then we went over, but we'll be back to the normal schedule next week. So with that, thanks again, Alina, for walking through all this, and really appreciate you taking the time.
Thanks, Dan, for the opportunity. Was great to cover this topic.
Awesome. Awesome. Well, with that, I think we're done. So until next week, so long.
Bye.